Thanks everyone for coming. Today's speaker is Yefi Yu, and he received a BE from Nanjing University of Aeronautics and Astronautics in Nanjing, China in 2018. And then he did his PhD degree at University of Texas, Arlington, under the supervision of Dr. Chao-Kun Liu. And I think he just graduated just recently, last month or two. And he will be an assistant research professor at University of Texas at Arlington after he finished, which is now. He's published more than 10 papers and participated in writing several chapters in 3 books. He attended and gave presentations at ASME and AIA conferences, and his research interests on the vortex identification, Liutex core lines, and Liutex dynamics. And so today he will present on Liutex and 3rd generation vortex definition and identification. So please go ahead.
Okay. Thank you, everyone, and thank you for your kind introduction. I feel very honored to have a chance to speak here. The topic of my today's presentation is Liutex and the 3rd generation vortex definition and identification. The outlines of my presentation is shown on the screen. The theme of my presentation is that vorticity is not a good representative of vortex, and the 2nd generation vortex identification method are also not accurate. And our new new definition, Liutex, is the best method right now. So I will start with the 3rd generation of the vortex definitions. The 1st generation is vorticity-based definition, dated from Hanford in 1858. According to 1st generation, people usually use vorticity filament to display the structure of vortex. And then after people realizing the problem of the 1st generation, 2nd generation method, including delta criterion, Q criterion, lambda C criterion. However, this method shares some common problems, which I will detailedly illustrate later. And then we developed the 3rd generation. It's dated from 2016. It's basically we define a new vector to correctly capture the vortex of fluid. Okay, talk about the 1st generation vorticity-based definition. The question is, can vorticity represent vortex? Well, the answer is no. Vorticity fails to capture vortex, and it has been verified by many scientific and engineering applications. You can see this figure. This figure shows you the lambda vortex and the shear layer. But you can see inside the lambda vortex, the color is green, which means the vorticity magnitude is not big. And the red region is outside the lambda vortex region. So vorticity does not match our numerical simulation result. And another evidence is this still lambda vortex region. So the actual surface is the lambda vortex region, and the lines are vorticity lines. The color shows the strength of vorticity. You can see the red color is outside the vortex region. Well, inside the lambda vortex region, the color is blue, right, which is smaller than red. So this is another evidence vorticity is not a good indicator of vortex.
I'm going to change it so it's a little larger for everybody. Sorry.
Thank you. And counter example. This is a counter example of vorticity. Well, this figure shows the coda flow. Right, coda flow are straight flow. We can calculate the vorticity of this model. The vorticity is -c, which is not 0. However, we know there's no vortex in coda flow. So after realizing the problem of vorticity, people like dedicate themselves to find some better method. Some of the well-used method are listed in the table, including Q criterion, delta criterion, lambda 2 criterion, and the lambda CI criterion. But all these methods are better than vorticity. However, they share some common problems. The first problem is the second generation methods are all scalars, and we know vorticity has the information of we know Vortex has the information of rotation axis, which is a vector. So scalars cannot tell you any information about a vector. Second problem is they are all contaminated by shear, so they are not accurate, the second generation method. And since they are all scalars, to show the vortex structure, we need to use ideal surface, which requires a threshold. As the choice of threshold may cause the confusion about whether the vortex break down or not break down. The different threshold will indicate different vertical structures. You can see the figure 4. So these three figures are about the same time, same situation, same case. The only difference is the left figure use negative 0.017 as the threshold. The right figure use the negative 0.003 as the threshold. If you look at the left figure, you may conclude the vortex breakdown, and if you look at the right figure, you may have another conclusion: the vortex is continuous. However, the vortex structure should be unique, right, in nature. And this confusion is caused by thresholds.
Yes.
Yes.
Not that familiar with the flow configuration. What kind of flow is are you referring to?
Flat plate boundary transition. Flat plate boundary transition. Oh, the flow goes through a flat plate.
So it's within the boundary, the vortex structure in the boundary layer.
Boundary layer,
Yeah.
from laminar to turbulence.
Yeah.
I see. And which way are we viewing from top?
From top.
Okay.
And we have a movie, so to show you the different structures with different ISO threshold. On the movie, we can see using different structure, we get different using different threshold, we get different vertical structure for the same same case. Okay. So then we introduce the third generation. So the idea indicator of vortex should be a vector whose direction is the local rotation axis and whose magnitude is related to angular speed, right? That is radians per second. And we call the vector we find Liutex. So first we introduce how do we find the direction. So the local rotation axis direction comes from the idea that a local fluid rotation axis should be a vector that can only have stretching or compression along its length. This idea is also correct for rigid body, not only correct for fluid. And if we express this sentence in mathematical language, that is dV is equal to gradient V dot product R is equal to alpha R. Alpha is a number. dV is the increase of the velocity. So the increase of velocity is still along the direction of R. That means it only has stretching or compressing. And from equation 2, we can see apparently R, which is the local rotation axis, is the eigenvector of the velocity gradient tensor. And since one eigenvector can have positive or negative directions, right, to further constrain the unique direction, we apply another condition. Vorticity dot product R is greater than 0. That means the angle between vorticity and the local rotation axis should be an acute angle. As for the rotation strength, so we extract rigid rotation part from the velocity gradient tensor and use it defined as the rotation strength. So for simplicity, we discuss a 3D situation since we can simplify 3D to 2D by letting the z-axis parallel to the local rotation axis, and we already know how to find out local rotation axis. So we first figure out what is the feature of the rigid body rotation matrix. So if a rigid body is doing fixed-point rotation, its velocity gradient tensor is shown in equation 4. Right? So its feature is the diagonal matrix are all zeros, and the off-diagonal entries are opposite to each other. Right? That is the feature of rotation, rigid body rotation, velocity gradient tensor. And we use the example to show you how do we extract rigid body rotation from a real velocity gradient tensor. So suppose we have equation 5 as our quarter flow velocity gradient tensor, and the traditional idea is the Cauchy-Stokes decomposition, which is a misunderstanding. So the way they generate or they get the matrix satisfying rigid body rotation is shown in equation 6. They do 1/2 gradient minus the transpose of the gradient, right, which get 0, 1, 0, negative 1, 1, 0. Although it satisfies the feature of rotation matrix, but it's an artificial rotation. It does not match with the fact. Actually, it misunderstands shear as rotation. Right? In equation 5, we see that is a Q shear velocity gradient tensor, but after applying Cauchy-Stokes decomposition, it misunderstands shear as rotation. And what do we do to extract rigid body rotation? We okay, so if you look at the equation 6, you can see it's actually taking average of the 1, 2 position, and it's taking average of -2 and 0, right? We get -1 and 1. So vorticity taking average. But to extract the rigid rotation, what we need to do is choose the smaller one. We need to choose the smaller one. So I mean the magnitude, which the one that has smaller magnitude. So we have 0, -2. 0 has smaller magnitude. So we need to use smaller one as the angular speed. That is the rigid rotation. It does not contaminate by shear. And the equation 5 is the velocity gradient tensor of quarter flow, and we know quarter flow has no rotation, right? So our way is correct. The vorticity way is wrong. The traditional way is misunderstanding. And another problem we may face is, even though we restrain the z-axis as the parallel to the local rotation axis direction, the choice of coordinate can be various. And we know the velocity gradient matrix is the tensor is unique, but the matrix can be different, right? The expression of matrix can be different. Matrix depends on the choice of coordinates. So if we use different coordinates, the number in the matrix can be different. So then we can have a problem. So maybe in different coordinates, the off-diagonal elements are different numbers. To solve this problem, what we do is we choose the smallest magnitude among all possible among the velocity gradient tensor in all possible coordinates. So like the relation between the gradient in the coordinate rotating from another coordinate and their relation is shown in equation 9. So by rotating the coordinate, we get a new coordinate, and in the new coordinate, we get a new velocity gradient tensor matrix. So the real Liutex magnitude is the smallest one among all partial u over partial y and partial v over partial x in the all possible coordinates. Liutex magnitude is defined as twice angular speed. So that number is angular speed, and Liutex magnitude is defined as twice angular speed, since vorticity is twice angular speed for rigid body. And we have an explicit formula to calculate Liutex magnitude. We don't need to do this rotation. So we find a explicit magnitude, which is shown in 11, equation 11. So in the formula 11, it has vorticity, it has Liutex direction. The lambda CI is the imaginary imaginary part of the eigenvalues of the velocity gradient tensor. They are all Galilean invariant, so they are independent on the choice of coordinate. So actually, we can calculate the magnitude very quickly. Okay, so finally, Liutex is defined as its direction is the eigenvector of velocity gradient tensor such that vorticity dot product, the direction is greater than 0, and the magnitude can be calculated from this formula. And then we verify the correctness of Liutex. Figure 6 shows the vortex region and the vorticity lines and the Liutex line. In figure A, it's the vortex region and the vorticity lines. The blue lines are the vorticity lines, and you can see vorticity lines are not aligned, do not align with vortex. But on the right figure, the red lines, Liutex lines, is aligned with vortex. You can see the directions aligned with the vortex direction. And Quincy did analysis compare Liutex with other methods based on the land ocean vortex, which has analytical solution as shown in equation 12. In figure 7, the blue dashed circle is the analytical vortex region from the analytical solution, and the figure A is the vortex region indicated by vorticity. Figure B is the vortex region indicated by lambda CI, and the figure C is the vortex region indicated by Liutex. So from these three figures, Liutex is exactly Liutex exactly coincide with the analytical solution.
Sorry, can I just
Go ahead. Go ahead.
finish your thought, and then I got a question for you. Oh, actually, I'm on that plot, actually.
Yeah.
So the vectors that are being plotted, is that the velocity vector field for?
Oh, the vector are velocity, yes, velocity vectors.
And so what is, my eye has a hard time seeing why the blue line is drawn where the blue line is in that velocity field. So can you give me a little bit of a explanation for what boundary is detecting in the velocity there to be able to make that distinction?
Well,
The blue line is what I call, right? The blue
that's the vortex region indicated by
from 12.
yeah from 12. It's
This is the analytics.
yeah.
But why physically is it why is it at that, radius of whatever that radius is there, and not epsilon further out or epsilon further in? And from the velocity field, I don't see any different. Maybe it's just the way it's plotted, but I certainly don't see any reason why it should be there.
Let me remember. How do they
From the 12 to on from on.
Yes, I can. Well, I think I have their paper. So yeah, I may forgot how do they like.
So that's fine. We can talk about it afterwards. You can go on with
the exact solution. Yeah, that's the exact solution. I find how do they like figure out the vortex region from which.
Maybe related to Mike's question, what's the green? The
Green is yeah. We calculate the value of these three methods, and we draw the green. Right, you see the legend. That's the value. Yeah.
So that's the different like this is the Liutex value. That one's the lambda value. That one's the vorticity value.
Yeah.
And the only thing I can see, I mean, maybe related, also related to my question, is that within that blue region, it seems that there's you know, whether you call it shear or vorticity or whatever, the wind changes, the magnitude changes with radius.
Yes,
And the outside it's constant. And I'm not sure if that's the
oh, you got way better eyesight.
Something like
finally.
outside like invisible, inside like a viscous core. They call viscous core.
I see.
That's the first term. The second term is about invisible. I think there's a non-ocean what they have exact solution. So the blue line is according to the formula 12. So 12 is the formula they got the exactly core by the blue line. So according to the formula. So you can see that what is sort of clean. They're much bigger area than this blue line. As Q is small. They lost some. Lambda CI, little bit, but not Q. And only the Liutex, they use Liutex, what we call all Liutex. And it is exactly matched the Atlantic Sun, exactly the same as Atlantic Sun. Match. And this is the core blue line is from the 12, get it? Yeah. Inside is invisible, with viscous, the outside is invisible.
And we can also compare the rotation period predicted by this method. So for analytical period is calculated from equation 13, and the other period is calculated from equation 15. So in figure 8, the gray region is the analytical solution, and this green, right?
Gray, not
Yeah,
green.
gray is analytical. Inside the gray, it has a line. I think it's like green lines, a green solid line. That's the Liutex result, and the others are the vorticity and the lambda CI. So only Liutex, the rotation period estimated by Liutex matches the analytical solution. Okay. After defining Liutex, we can discuss the problem of vorticity. So well, we know vorticity works very well for rigid body, but it does not work well for fluid. So the core reason is vorticity can misunderstand shear as rotation. So from our previous example, we can see the 0, -2, 0, 0 is the pure shear matrix, but vorticity thinks it's doing rotation with angular speed of 1. So vorticity indeed is the sum of rotation and shear. And if shear is 0, right, which is the case for rigid body, then vorticity is equal to rotation. Because for rigid body, there is no shear deformation. Then in that situation, vorticity is exactly rotation. But for fluid, we have shear. Vorticity is not accurate. We also define the principal coordinate and the principal decomposition. Because velocity gradient tensor is unique, but the expression of tensor in coordinates is different, right? So in different coordinates, the matrix is different. So our purpose to define principal coordinate is to solve this problem. Well, we do some rotation to define the principal coordinate, and the benefit of finding principal coordinates is on the principal coordinator, the velocity matrix is always like in the format of equation 19. So on the principal coordinator, the velocity gradient tensor is always like in the format of equation 19, where lambda CR is the real part of the complex eigenvector, and the lambda R is the real eigenvector R, right? -1/2 R. R is the Liutex magnitude. And the benefit of having this format of velocity
What is the epsilon?
epsilon cathexis are shear. Epsilon catheta are shear. So the benefit of having the format equation now is we can easily decompose the velocity gradient tensor into shear part, rotation part, stretching, compression part, and the shear part, as shown in equation 20. And the physical meaning of each part is very clear.
But that's different from
Yeah, it's
Cauchy-Stokes.
different from Cauchy-Stokes decomposition.
Yeah.
Next, we talk about the omega vortex and diffusion criteria. Well, the idea of omega method is vortex is a region where vorticity overtakes deformation. So omega, the formula of calculating omega is shown in equation 21. But the reason we add epsilon on the denominator is to avoid the denominator being 0. And the benefit of omega is it is normalized. You can understand it as a normalized vortex identification method. So its advantage is easy to perform. You just apply the formula, and the big advantage is selecting the threshold. Like for Q or lambda Ci, right? For this method, the proper threshold can be various from case to case. But for our omega method, since it's normalized, the proper threshold is always around 0.52. So like for different cases, you can start to try different, select the threshold as 0.52. You may just increase a little bit or decrease a little bit. You can find the proper threshold. And since our this method is normalized, we can capture both strong vortex and a weak vortex simultaneously. This method, the modified Liutex-Omega method, is improved from omega, since omega still has shear contamination in it. So the modified Liutex-Omega, we remove shear influence from omega method based on Liutex method, because at the time we developed omega, Liutex is not developed, so it's still contaminated by shear. But after we define Liutex, we remove shear from the omega method. So this method combines the benefit of Liutex and omega method. So we use the principal like the velocity gradient tensor in the principal coordinate to calculate the omega method. So we can find in equation 25, we can find the red terms are the shear part, right? We already decomposed principal decomposition, so we know these terms are shear part, and then we just remove these terms, and then we get equation 26. And the alpha and beta can be obtained from vorticity and the Liutex direction and the imaginary part of complex eigenvalues of the velocity gradient tensor, as shown in 24 and 27. And our final explicit formula is 28, equation 28.
What is each term? The physical meaning of each term?
Physical meaning. Vorticity, omega is vorticity. R is Liutex direction. Lambda Ci is the imaginary part of complex eigenvalue of velocity gradient tensor. Lambda Ci is the real part of the complex eigenvalue of velocity gradient tensor. Lambda R is the real eigenvalue of velocity gradient tensor.
Epsilon.
Epsilon is a small number added to avoid the denominator being 0. Okay. And figure 9 shows you the benefits of this method. So in this figure, we capture both weak vortices and strong vortices. So for other method, if you want to capture the strong vortices, the vortices around x 430. So if you want to capture vortices around 430, the threshold should be, if you use Liutex, the threshold should be 0.07. If you use Liutex, if you want to capture the vortices in around x equal to 340, then your threshold should be choose as 0.005. So it's 10 times. So you cannot show the structure of weak and strong vortices in one figure. But this method it captures both strong and weak vortices. And the next method I like to introduce to you is the Liutex-Colline method. Even though we developed some new concepts, we still use isosurface to show the vortex structure. Right? The ideal situation is we can use a line to show the vortex code. Right? And that's the reason we developed Liutex-Colline method. Figure 10 shows you the effect of this method. So the green isosurface shows you the vortex region, and the red line is the Liutex-Colline. Right? That shows you where is the Liutex code. The definition of this method is Liutex-Colline is formed by points that are located at positions that satisfy equation 29. Gradient of Liutex magnitude cross product Liutex direction is equal to 0, and also the Liutex magnitude should be greater than 0. So our idea to define this concept is that the Vortex-Colline should be local maximum of Liutex. So that is in the plane perpendicular to Liutex direction, it reaches maximal Liutex magnitude. And since that in that plane, the Liutex magnitude gradient should be 0. Since that is maximal and it should be a critical point, right? So the gradient should be 0 in the plane. And for the whole space, since the magnitude is the gradient is 0 in the plane, so its only direction, possible direction, is perpendicular to the plane. Right? In the plane, the gradient is 0. So the only possible direction, gradient direction, is perpendicular to the plane. And we know the plane is perpendicular to Liutex direction. So the gradient should be parallel to Liutex direction. Right? And the parallel is expressed by gradient R cross product R is 0. Right? Cross product. If cross product is 0, that is parallel. So that's the reason we define Liutex-Colline like this. And then the Liutex-Colline can answer to the question whether the vortex breaks down or not break down. If you use the isosurface, the vortex looks like breakdown. But if you draw the Liutex-Colline, they are still continuous. They are one vortex. Right? The blue lines are the Liutex-Colline. And also we can use the color to represent the strength as the vortex code. Red color means it has strong vortex. Blue color means it has weaker vortex. So we can see in the lag region the vortex is strong, and the blue color region the vortex is small, is weak. It shows you the strong and weak vortex on the vortex code at the same time.
So if you choose threshold, for example, threshold, threshold, then all the blue color will be disappeared.
Right.
So vortex will be broken down.
Yeah.
Or you can pick larger, then the green part also disappeared. The even more vortex breakdown. So breakdown is caused by threshold, not by physics. Not by physics.
If your threshold is big, only the red part will leave in your isosurface. But if you choose a small threshold, the green part or the blue part will contain in the isosurface. Oh, Then that's our some new finding, but not very mature. We find some new fluid kinematics. We find that the divergence of velocity gradient tensor is equal to the gradient of divergence of velocity. So by doing the calculation equation 30, we find the conclusion equation 31. And we know for incompressible flow, divergence of velocity is 0. So the divergence of velocity gradient tensor is always 0 for incompressible flow. That's our new finding.
No, first, what I mean physically, what I mean. Your physics, what I mean. 31st, yeah.
31st, the physically means
No, their data is what? Their data is what?
delta is
It's divergence.
the divergence.
There is what?
Delta V is gradient velocity.
Yeah, that's what I mean. That's the velocity gradient tensor is divergence. Is what?
That's
It's
the
TR.
force.
What
That's the
TR?
force. That's the force.
The TR is what?
Huh?
TR is what?
TR is the trace.
Trace
of
what?
the trace.
Trace what?
Trace of that's the that's partial U over partial X plus partial of velocity gradient.
It's summation of the stretching.
Yes. Yes.
The stretching term.
Yeah.
So the gradient tensor divergence, it is gradient of stretching. But that's a new law.
Yes.
Sorry, I did wrong. Go ahead.
Wrong.
Yeah.
Bad.
Battery is on there.
Yeah. Yeah.
What is why are they switching? So as I just said, we try to go ahead.
That was smooth. Consider.
Sorry about it.
Then we can use this result to find some new format of the governing equation. So for incompressible flow, since divergence of velocity gradient tensor is 0. So if we add that term or subtract that term will not make a difference, right? Because it's just 0. I mean this term, right? This term is 0 for incompressible flow. Oh, that did not see the mouse. I mean this term is 0, right? For incompressible flow. So you add one term or subtract one term, it's not make a difference. And so the divergence of this can be the divergence of the string, right? Divergence of it plus its transpose. It's also equal to itself subtract its transpose, right? So in equation 32, it's a string. Right? On the right hand side, it's a string because it's itself plus its transpose. And in equation 33, it's the vorticity because it's itself subtract its transpose. Mathematically they are equal, but it has some difference. Is in equation 32, it has 6 elements, right? In string, the symmetric matrix, we have 6 elements. But for vorticity, it's anti-symmetric. It only has three entries because the diagonals are all 0. Right? So the variable number is reduced. And the original non-Stokes equation can be written as in equation 34. And we can since we have equation 32 and equation 33, the equation 34 can be rewrite to equation 35. They are mathematically equivalent. But the difference is in equation 35, we use the last term is related to vorticity, the antisymmetric. And in equation 34, the last term is related to strain, the symmetric.
Happiness 34 is now it's 30 questions.
Yeah, that's now it's
35 is not.
our new equation.
So what's the advantage? Why doing that?
Oh, well, because we reduce the number of variables. In anti-symmetric matrix, we have 3 variables need to solve, but in symmetric matrix, we need to solve 6 variables. And for incompressible flow, we can further simplify the equation since we know it's 0 for incompressible flow. So the our new equation becomes equation 37. The original equation has 6 terms in the velocity gradient plus velocity gradient transpose term, but our new equation only has 3 terms since we use velocity gradient subtract velocity gradient transpose. And some result we compare our the result calculated by the new governing equation with the original one. In this case is for 2D backstep laminar. Also, we did simulation for turbulent flow in an S dot. And the computational results by the new governing equations are almost the same by non-Stokes equation. Mathematically, they are equivalent, and we do the numerical simulation. They are almost the same as well. Some reference. And thank you for your time.
And thank you. We have time for questions if anyone has one either in the room or online.
I have a question.
Yes.
I mean, the original vorticity formulation, one advantage is that you can decompose your fluid dynamics equation into, say, divergence and vorticity. And I think it's called Hamilton's decomposition, right?
Yeah.
And then there's a result.
Yeah.
That's right. So as a result, I mean, one advantage that can be the vorticity can be treated as as a primitive or state function or a state variable that you can solve in the fluid dynamics. So now with Liutex, do you have can you formulate that in a similar way that you solve that as a state variable? So the Liutex is a state variable.
That is a good question, but I think this is what we call Liutex dynamics, not vorticity dynamics. People usually call it vortex dynamics. It's really vorticity dynamics because they're mixed. But now we say we need to develop Liutex dynamics. That's really exactly vortex dynamics. So that's we need to give the governing questions. That's what I asked him to continue to work in the UTA. So that's we try to hire him. So that's the.
So try to formulate.
Right. Deal with the dynamics. This I think is important for the turbulence research. Because turbulence is nothing else but vortex. What is this? The vortex is really exactly the same as the Liutex. They are same thing. But people misunderstood there's a vortex equal to vorticity. That's in the history. But it's not. Vortex is exactly same as the Liutex. They are equal to each other, I think. So the turbulence is the vortex. So that's what I say. Well, maybe too aggressive. The too aggressive. Without the vortex, how to study turbulence? What means turbulence? Without the vortex, how to do? What is vortex? Vortex is nothing else. Liutex. That's what I said. So we want to develop new dynamics. We want to develop turbulent dynamics. We want to develop new fluid dynamics. That's what we plan to do. As I try to persuade him to stay in UTN. That's what we were trying to totally rewrite history.
So maybe it's related to the last part. Is there any, I mean, I understand you rewrote the equation. Is any part in this equation kind of related to Liutex?
Let me, this one is not that deep. So that's really mathematical, the same. So people use, now it's a question for more than 100 years, right? So the same is 37, 36, exact mathematics, it's the same. Then what's the difference? So difference is what? And now it's three question doesn't have what is it at all. Look at the now it's three question. That's without what is it at all. But number 37 without the string at all. So now it's without what is it? Our new equation without string at all. Then why use what is it? The advantage of number one, 6 elements becomes 3 elements. Number two, what is it has 2 parts, Liutex and shear. There is no reason to assume the viscosity coefficients are same. So that's we call the new fluid dynamics. Because we didn't decompose the second term, that's in the 37. The last term of 37 can decompose the 2 parts, Liutex and shear. Shear has viscosity, everybody knows. But why Liutex has the same viscous coefficients? That's law proof. So that's where I say we need to develop the new fluid dynamics.
And another reason of vorticity is Galilean invariant. And
Again, that's another advantage because what is the kind of invariant, not shear, not a strain. Strain is changed. What is never changed. So that's good for the for the unstructured grids, for any kind of grids, because they're not changed. No matter your coordinates have to change, they don't change. What is it doesn't change? You just take projection. When you get any kind of coordinates, you just say what is it? Take projection. So that's another advantage. This is the Galilean invariant. So well, this is not a benefit too much. That's only benefit some. That's not our purpose. Our purpose is decompose the vorticity, the 2 parts. We need to find each part. What is the force they generate? We know the shear will generate shear force. What is generated by Liutex? What kind of force they generate? So we need to discuss. That's what we call the new fluid dynamics. So we hope, but this hard. But when I get the NS, they got a eager grant with I cannot promise that we develop new fluid dynamics, but we try. As I said, yeah, we try because apparently we have to decompose. We shouldn't use the shear, the symmetric shear. But that's by Stokes' assumption. Stokes' assumption is that stress is proportional to the strain, right? By mu is the constant, is the isotropic any directions, but it shouldn't be metric. But they just use one constant. Well, those Stokes' assumption, well, we don't know is correct or not correct. Well, it looks like to me it's correct to the to the laminar flow, but apparently it doesn't. It's not correct with turbulent flow. Why is not correct with turbulent flow? Because turbulent has vortex. Vortex what? It's a Liutex. Why didn't consider Liutex? It threw away at all. So how to get down equations for turbulent flow. That's really a problem. You always miss the important part. That's a vortex. Vortex what is Liutex? Well, you missed that. So that's the reason we cannot calculate exactly if we use Navier equation. That's a problem caused by Stokes assumption. So that's what I think. Yeah. That's well, we can discuss. I hope we can, discuss with experts so we can. That's a big historic issue that we try to develop some equations.
If you do that, you'll have no problem getting tenure.
For me.
No, for him. Remember, right?
No, I try to ask. He's young. I'm old. I graduated from Denver. So you see them. So I'm familiar with this area. So,
You should maybe attend, do you know about the SHINE meetings, solar heliospheric? They have a big turbulence usually presence. And so that might be something that you might be interested in going and talking to folks.
Yeah, they're like the leaders of the MHD church. That's why Bill Matthews is always probably a big presence there.
Yeah, he's always there.
Yeah, you can introduce us. Yeah, but we are basically on the theoretical part. So really, we don't have experiences in the real problems. Like,
Bill's pretty theoretical.
Yeah, they all are. I always think of turbulence folks as being very.
Okay, that's good. Yeah, we hope some to collaborate with some turbulent people. So that's one. But actually, it's two parts. One part is visualization. That's I think NCAR might be interested. There's some group with some, sunstorm, the solar storm, something like that. They try to get the vortex structure. Yeah, so that's called visualization.
Yeah.
We don't do any calculation. So, but the other group could be turbulence, study group. So it is not only for the visualization, that's really for the science.
Mm-hmm.
So that's one.
There might be some applicability to also magnetic fields, right?
Well,
the equivalent would be kind of something like a flux rope, which
that's, I guess,
similar to what you're trying to.
that's, I guess, but let me see that, for the magnetic field, there's some difference from fluids, because magnetic, electrical is magnetic, but it is similar to the velocity and vorticity, right? Whereas you can use Biot-Savart equations or something like that. It is a little bit difference, maybe similar, little different, because fluids have the viscosity, especially in the boundary layer. So this could be some kind of different from magnetic field, but I believe the whole universe have vortex. That's what I say. So what is vortex? As I said, exactly same equal Liutex. So the magnetic, field can use as well. That's what I say. I'm not sure to get a lot of benefits. I'm not sure, but I'm sure you have vortex. That's what I say. Anymore, we hope. Then we hope we use our method to benefit a different area. That's the EAGLE program for. They try to support the new ideas. So we are in the infant stage, so we very early stage. So we hope more people to use it. So that's what I say. We also have the workshop. So that's the announcement. I think everybody can get one. I think without dispute. Yeah. So actually we have many. Really we have 6 conferences already.
Yeah.
But people don't know that. Yeah. A big different area. People don't know this. Yeah. So.
Very interesting. Thank you.
Any more questions? Some, okay. Cannot hear.
I think maybe not.
No more question? Oh. Okay. No more question.
More question. Again.
Welcome, everybody interested because the talk is very, one time. So we can discuss it if interested. If we have